Hi Roboticist, today we're gonna talking about get the position of the object that we have created in Gazebo. So we are still continuing our OpenCV Basics for robotics, and you will learn how to get the position of the red object of our simulation environment in the real world. So basically, when we are going to change the position of the object, the camera displays automatically in the image the position that this object has in the real world. So you are going to get the position in XY of the object with the respect of the frame of the real environment. So before to start, make sure to subscribe to the channel if you like this kind of video, and if you want to have a deep dive and get in 5 days from a beginner to intermediate level to have a good understanding of this kind of video, check out the link in the description down below and my online courses. You can see a 50% discount for get more than 7 hours of deep dive in ROS. So now let's get started. So here I open my simulation environment. So I'm gonna remember you that the camera is gonna be here. This is the Python script that we have done in the last video. I'm gonna put the link in the description down below, where we have created a red mask and surrounded the object that the camera sees in a blue box. So let's run it again and okay, here we go. The program has detected the edge of this object, and it has surrounded here. And what is here is the coordinate in this frame, in the camera frame, in the OpenCV frame, where here this is gonna be the y coordinates, and from this direction, from left to right, is the positive x. And here, the center of this rectangular here is gonna be round about 399 and 339. So you can check here the real position. Okay, so the objective that we want to achieve here is to display at the center of the object detected the real coordinate that this object has with the respect of the frame of our environment. And I remember you that the real zero coordinate is here. So in red you're gonna have the positive x, in green you're gonna have the positive y, and in blue you're gonna have the positive z. So we know from the Kobo test, I'm gonna put the link in the description down below, that this object is placed with the center in x1 meter, y 0 and z 0.5. Okay, so we are gonna test the real value considering this. So this displays the real position of the object. And the purpose of doing this kind of thing is that we want to use that position and send to the robot in order to get what the position is and create an inverse kinematics pathway that allows the TCP of our robot to grasp our object. So at the end, the objective here is that in the cobot test package that we have already created some videos ago, in the pick and place gazebo, we have asked the robot to pick the object in the position that we have set up previously. So if we are going to go in the pick function, so, and this is the position where we asked our TCP to go in order to pick the object. And our aim is to get this coordinate from the camera that detects the edge detection using OpenCV. So we are gonna use OpenCV, I repeat, to get the real coordinate of the object and pass to the pick function of our pick and place application. Okay, let's get started here. First of all, what we will need to do is to simplify as much as possible our problem. And in order to simplify, we need somehow to understand better our application, our environment. So let's go into the simulation, and the first things that we can consider is that the z position of this object will be always the same. So it will be always at 0.5, even if we place and we move, our object somewhere else. So if we translate our object, for example, in the positive y direction, let's see what's happened. You can see here that, here the OpenCV detects our object, and the position of this object will be always 0.5 meters roundabout. So this is the first thing. The second thing is that due to the fact that the camera is positioned here, you are gonna have the center of this rectangle that is an offset with respect of the top of the object, and this if we convert this coordinate into the frame coordinate of our environment, we are gonna get a different value. So we will need to find a way to somehow downsize our application from 3D to 2D. And one idea will be, for example, to place our camera on top of the pick object. So instead of being in this position, we're gonna place on the top. Okay, so let's do that. Okay, here we go. Here I am in the Kobo Mimic chakra file, and this is the new position of our camera. So I change the position in these coordinates, and I changed the pitch angle of our camera. So now if we run our simulation, it will be on top. Let's test it. Okay, you can see that the camera now is on top, and if we run our viz, here we are. We get the point cloud value, and we have this square that is our top side of the object. So if we run our OpenCV codes, what we're gonna see, well, actually we don't need this, so we can comment this out. And now we should see the top of the of our object. And here we go. We have the top of our object. We have displaced the x, y coordinate with the respect of the OpenCV frame that I remember. Here is the positive y, and this is the positive x. And so it's working. But this is not enough. Why that? Because if you are perfect on the top, well, you can see that the center is gonna be the center of the object. But what happens if we display or if we move this object, for example, here in the positive x direction with respect of OpenCV coordinate? Well, let's try. So we are going to select this object, and let's put it here. Let's see what's happened. Here we go. You could imagine that since this is a normal camera, optical camera, you're gonna see the perception, the depth of our object. And here now the object detected using the box inscription is completely shifted, and the center is gonna be shifted as well. Of course, because now the center, it will not be this one, but now it's this one. And for our application is not good, because we want that the TCP, if we are looking on the 2D, is placing here, so it's gonna grasp in this position, and we expected the gripper to be somehow here. Okay, so this is not good, and we should find a solution for that. So what we can do? Well, first we can exploit from our advantage the light of the environment, and we can see that on the top the light is lighter, let's say, with the respect of the body. And this is something that we can exploit by adjusting the HSV maximum and minimum parameters of our code to create a mask that is only detecting the top. And from that moment on, we will be able to detect the center of this square that in 2D will be the center of the object itself in 2D. So we're gonna get the X and Y coordinates. So let's do it. Okay, so we will need to find what will be the minimum red and the maximum red. So this is the minimum H parameter, this is the minimum S, and this is the minimum V, and here the maximum of the top side of the object. So how we can do? Well, I remember you that we have created a few videos ago the get HSV by clicking with the mouse. So this algorithm is able to get the HSV parameter of the pixel that we're gonna click with the mouse. So we will need to get an image first. And what we can do is to write a Python code where we write the image that now is getting the camera, and we're gonna place in a file. So let's do that. Okay, here we go. I have already created this script, so I just copy and paste. This is not important because we have already tackle how to save an image, but basically this is the main, and always the same approach. The difference here is that I created this folder path, and then what we are getting from the camera will be saved and named object new position in the folder output here. Okay, let's run. Okay, this is the image that the camera got, and if everything worked fine, this image has been saved here in object new position.jpg. Let's check it. Okay, this is the image saved, and this is the value that we can see. Okay, so this is working, and what we can do here is to pass this image to the Python script to get the updated HSV value of the top. So we will need to change this, and we will need to pass object new position. Let's run. Okay, here we go. If we click here on the top, you can see on the terminal that is displays the value of HSV where I'm clicking on. Okay, so if you note all the value from the HSV camera, and I'm always clicking in the area where I'm most interested in. Okay, feel free to play with this code and find your value minimum and maximum in HSV. I already did it before, and what I found in my environment is this one. This value may change with respect of the position of your camera, so pay attention to that. It's not, they are not absolute value, they are relative to the position and the light that you have in your environment, in specific in your application. Okay, so a better approach will be to create another file. Okay, so let's copy and paste. Here we go. Let's clear a little bit up this file. So this we won't need. Okay, what we need to do is to update this value with respect of the value that we have founded. So this is 0, this is 5, the minimum. I've seen that the top gave me a value of 20, and then this is gonna be 120. Okay, these are the value that I found. Feel free to use your tool to get those. So if we test, we will see that there will be a square, and the square will be kept even if we go in another position. Here we go. You can see here that with this new script, the mask that has been generated is always a square, regardless the position in xy where we are going to put our object. Let's test better. So let's move this, for example, in the roundabout in the center, and nothing should change. Okay, you can see here, even if we have this part, this portion here that is detected from the camera, this is not seen from our mask, because we are always keeping the top, and the value here, the pixel position, is updated. So let's see if we go from the top. We are lucky, and we keep to have, yes, we keep our square, so meaning that the value of hsv from the top doesn't change if we change the position, as long of course we are in a small area. Okay, I think that is working. So we can pass to the next topic, and here is displayed the center of the top square. Okay, and this is displayed in a pixel with the respect of the OpenCV frame that I remember you that is gonna be here positive y and here positive x. But if we compare with the origin frame of our environment, if we see from here, we can see that from this position, from the bottom and from the bottom to the top, it will be the positive x. So this is here. So in fact, if we go to the positive x, the object is moving upwards. Okay. And if we go from the positive y, is moving here. So we need to have some kind of conversion between the frame of OpenCV and the frame of our environment. And so I remember you that here is gonna be the positive y of OpenCV and positive x. And here is gonna be the positive x, and here is gonna be the positive y. So this will be displayed not the center in a pixel, but will be displayed the position in the real world. Okay, before to pass in the coding section, I think that is better to make some understanding in order to do not make any confusion. I hope that after this explanation, the implementation in the code will be much easier. So here we are. We have our object with the top side view. These are the coordinates in OpenCV in green, positive y and positive x, and this is these are the coordinates in the world, positive x and positive y. So we have our object here. And we know already the position in the real world, that is gonna be x0 1000 millimeters, so 1 meter, and y0. And if you run the OpenCV code, you will see that the center in terms of pixel will be 399 and 300. Okay, so the first things that we need to know is how to run a conversion between pixel and millimeters. And how we can do? Well, we just make a ratio between the width of the object that we have detected, and we're gonna see how to get that, and compare with the real millimeter of our object. And we have set up an object of 20 millimeters, and we have created that as a collision object in our Cobot test package. okay? And here, if we move, let's say, the object on the top right side of our image in OpenCV, we are gonna get the coordinate in pixel and the coordinates in the real world, that these are the ones that we want to detect, okay? So if we want to get x1, we need to run some calculation. So we know the coordinates here, we know the coordinates here only in the pixel size, and we know what is the distance in x between here and here, and this is gonna be x1 pixel that we know minus the x0 pixel that we know, divided the pixel millimeter conversion that we already know, it's here. So this will be the distance in x, or better in y, in the real world, expressed in millimeters. And if you are gonna do the same exercise here, you can get the position in the real world here, because this is something that you can calculate, because you know everything. Okay, here we go. We have the x0 pixel and the y0 pixel here, and it's gonna be 399 or 400 and 300. So let's put it here. Okay, basically, before the for loop to get the coordinates here, we can put here our static value. So here the x pixel center and the x pixel y pixel center, that corresponds to what we are seeing in the image here. Okay, these are the coordinates in our real world that are gonna be 1 meter or 1000 millimeters, 0 and 500 millimeters. Okay, now we need to run the pixel millimeter conversion, and we know that the millimeters of that is 20 millimeters. You can check in the cobots in the pick and place gazebo the object that we have created. So if we go in pick and place gazebo, in the function of the add collision object, we have created an object that we call object that is gonna be 0.02 meters, so it's gonna be 20 millimeters. Okay, what is missing here is how much those 20 millimeters correspond in pixel, and this is something that you can get from here. So with this function of OpenCV mean area rect, you are going to get the x center and y center in pixel, and also the width of this square that has automatically detected. And what we can do is, for example, since that it is a square, so the y and the h will be the same, we can print in our terminal. So first let's close this, and let's print it. Okay, let's run again. And here we go. You are gonna have 38 pixel, the one that we have seen in the slide before. I already knew it because I already tested before. So let's I put here the pixel millimeter conversion that is able to allows us to get the distance in the real world. So we are gonna have 38 pixel divided by 20, whatever this number it is. Okay, so now our aim here is to display on the center of the square the real values in x and y in the world, because we want to pass this object, this data to this pick and place application. And something that I didn't mention is that we need first to understand in which part the object it is, because this sign can be different. Because if the object is gonna be this one here on here with the respect of the center, this sign would change. It's an exercise that you can do. So I'm going to place the solution right away, but I would suggest to pause this video and try to get the real value. So I have commented here the value that we are not interested anymore, and I'm gonna place here the new code, and I'm gonna explain later on. Okay, here we are. First of all, we need to distinguish in which part the object is placed. And here is gonna be with the respect of the image on the top right side of the OpenCV image. And here you're gonna have the value y and x in the real world. And basically this is the same thing that we have seen in the previous slide, but put in a code. And I do the same exercise for x coordinates. This is the condition where the object is placed with respect of the center in the bottom right, and you can do the math here. This is where is put in the bottom left side of the image, and this is the top left side. Okay, here we go. Now you can read better. And now I put the text. So x is gonna be the coordinate that is gonna be displayed, and y is gonna be the y world coordinate that is gonna be displayed, and where we're gonna place it. We're gonna place at the center of the object in a pixel. So this gets the pixel value, and this is what you want to display. Okay, and this is the color and the thickness, and we are gonna put the circle in the pixel coordinates. So let's test it. So here is gonna be object detection from red mask world coordinate. Okay, as you can see here, these are now the coordinates in world coordinates. So this is gonna be the x 1 meter and 0. So let's move the object and see what's happened. So we are gonna place the object in the negative side of y direction in the real world. So let's displace. We're gonna place it here. So what are the values that we are getting now? So here we can see that we have 1000 and then minus 71 millimeters from here. So let's check. The pose in the real world, and here we go. We are gonna have 1 and yeah, this is displayed 77 millimeters. Here we get sorry, here we get round about 70. Okay, we have a few millimeters, but for this application it can be accepted. So let's displace somewhere else. So let's display here. So we are gonna have a positive y, and the x now will be higher than 1000 millimeters. Okay, let's check. Here we go. We are gonna getting 139 millimeters and 71 millimeters in y. Let's check it again. Here we go. We have 1041 and 74 millimeters, which is around about what we are getting here. Okay, that's all for today. Now we are ready to pass this value that we got here directly in the pick and place application, where now this camera is sending this value to the pick and place application, and this will be our first robotics deployments, because now our application will sense the environment. So before to leave you, I want to make a disclaimer on this application. We have used a depth camera to get an image, and we have created a masked color. Based on that, and based from OpenCV tools, we are getting the conversion between pixel and millimeters based on the mask that we have created. So and we have measure this object somehow, but if you wanna make an industrial application, please do not use a conventional camera for measuring object, because this is not reliable in industrial application, because you might have the light that is changing, and you don't have a correct hardware to do that, because if you want to make a real object measurement for quality control application for pieces of whatever shape, you should get a camera that, for example, has another hardware, has a telecentric lens, and also a light optimization in order to get as much as possible in a better way the pixel transition to get the object detection better. So for the purpose that we wanted to have, and I remember you that it wanted to have the position in X and Y, this is precise enough. So after the disclaimer, I want to thank you for staying with me till the end of this video. I hope that you get a lot of value with this tutorial, and why not, you can use in your industrial field or in your application for if you are a maker. Please subscribe to the channel in order to support me on the channel. If you want to make a deep dive, don't forget to check it out, the course that I've created. And don't worry, all this script will be updated on my GitHub. And as always, I'm gonna put the link in the description down below. And finally, I'm gonna wish you good luck in your robotic application. And as always, I'm gonna wish you to have fun. And let's see in the next video. And as always, keep learning robotics with ROS.